Dr. Siddiqui is an associate professor and associate director of graduate studies in the School of Engineering at the University of British Columbia, Okangang campus. She have completed her PhD at Cardiff University in Geoenvironmental Engineering and did her postdoctoral fellowship at the Geotechnical Laboratory of the University of Manitoba. As the lead researcher at the CFI funded Advanced Geometrical Testing Lab, she and her group developed new generation binder technology for roads and construction materials. Her team focused on transferring industrial byproduct into higher value binders that can adapt to future climate changes. She is an active leader of women in engineering and a co-chair of women in science and engineering at UBC. Due to her involvement in such critical activities, she has worked diligently in creating an excellent environment in her lab that is welcoming for female students, and she actively hires students from diverse backgrounds. With this, I welcome Professor Sumi Siddiqui for the lecture on upcycling of pulp and paper mill fly ash for road construction material.
Thank you, Shurvi, for a good introduction. Can you hear me well?
Yes, ma'am.
Okay, I'll just start sharing my presentation here. Is that good?
Yes, ma'am. Yeah, all good.
Okay, so good morning from British Columbia, Canada. I know it is good evening in India. So I'm happy to join here today to talk about the upcycling of pulp mill fly ash for rammed earth and road construction. And before I start, I would like to thank Professor Das for inviting me for this special series of lecture. So because we have been hearing that from yesterday, fly ash, but the fly ash we are hearing is the coal fly ash. Today, I'm going to introduce a different type of fly ash, which is a problematic waste material in Canada. We have many pulp and paper mills in Canada, especially in British Columbia, and they produce tons of fly ash. And this fly ash is going to the landfill, which is expensive to dispose those landfills, and it also takes a lot of space. The goal is to have use for this fly ash in different applications. And in this project, I have worked with the other teams from University of British Columbia, and there was a collaboration developed between the different pulp mills in British Columbia and the university to identify some construction related applications for this fly ash. So I will go over with the problem domain and then talk about what we have achieved from this project. So what we have here is we want to look into the waste generation in British Columbia and Canada. So that means what would be the different sources of waste that we see typically in the province of British Columbia and overall Canada. So common ones are agricultural waste. If I just use my laser pointer, agricultural waste, pulp and paper mill industry waste, and different waste coming from different energies industry. So this waste management and recycling is the goal, and transforming them to the value added product. How do we do that? Use this recycled product as carbon capture new materials. We want to target the less use of cement that Professor Das was just mentioning, and therefore it will have less impact on the environment, and find out a solution where we can apply those materials. So it can be either applied in the agriculture industry, going back to the agriculture industry as a composting material, or making building materials, or using it for roads upgrade and stabilization. So when we look into the waste stream coming from the pulp and paper mill, we just looked into what would be the different sources. And we identified a lot of different sources, but my goal was to look into the waste residue, that solid waste residue that we need to use it for construction applications. So we have identified three different types of ash. One is precipitated fly ash, which is finer fly ash. Then we also find out the multicyclone fly ash. And then the last one is the bottom ash. So what happens with that? this solid waste residue that produces in the pulp and paper mill, minimum of 1 million tons of ash produced per year in Canada, and it costs 20 to $50 Canadian dollars per tons to disposal of this fly ash. So we needed to find some application for these mills because they're losing money to dump those waste material in the landfill. One hand, they are losing money for disposal, and also there are environmental impacts because landfill space are valuable, especially in the North America, and finding a good space for landfill is always a challenge. And if you are filling up those landfill volume with large volume of this waste residue, then we are even making environmental impact in long run in a negative way. So we looked into what could be looked into the applications, what we can do about those material. It can be used as eco-friendly soil binder, soil fertilizer for composting, compost odor elimination, and also the construction material. So first of all is to find out the characterization. There are a lot of different ways to look into the characterization. So we started with the very basics, the physiochemical properties of the fly ash. We are calling it pulp mill fly ash, or the one in the first one here, precipitator fly ash. So PFA. So from now on, I'll be referring that to as a PFA. And this one, we have general, the elemental properties coming from the geotechnical laboratories, specific gravity, surface area, fineness, grain size distribution. As you can see, the sand-like particles are 24.8%, so almost 25%. Silt-like particles are around 53%, and the clay size particles are around 22%. Also, we have looked into the loss of ignition. pH value is 13, that is more on the alkaline side. And then we have electrical conductivity of these properties. We also wanted to look into the mineralogical composition based on the XRD. And we have seen the calcium hydroxide is much higher in percentage, which is 9.5%. And also calcium carbonate, the calcite, is also 62%. So which are good news for us because these are the good mineral that can be used for the construction material. And now by looking into the XRF analysis, then we looked into the bulk chemical composition. Again, we saw that the calcium oxide, silicon dioxide, those are the higher in percentage. However, there are some light element, which is very high. It was not possible to identify what are those elements, but it is part of the light elements under the XRF analysis. So this whole characterization of the fly ash, and the fly ash that I'm talking about is the pulp mill fly ash. We understand what are the properties we are dealing with, and then we looked into that in terms of the microstructure. And the second thing is about the toxicological properties, because these are the two things we have to look into if you're thinking about using them as a construction material or the road materials. The leaching would be an issue in future. So we have to know whether the toxic properties that we see in this material is within the limit provided or the standard provided by the Canadian Environmental Agency or the US Environmental Agency. So those two fly ash, that precipitator fly ash and the multi-cyclone fly ash, we have characterized using XRD, and we also looked into the toxicological properties and identified with respect to the BC water quality guidelines and the for the agriculture and also BC water quality guidelines for aquatic life. So these are the two reference points. And we saw that most of the properties are way below with the standard given to us. And also we compared that value with respect to the Portland cement. And most of the heavy metals we have seen in the fly ash, we found that those are either close to cement or much lower than cement properties. So these information give us a very strong feeling about the material, and we were excited to take this material into the next stage. So few important parameters we have identified from that. We have looked into the 3 different types of fly ash from the pulp and paper mill. First one is the precipitated or fly ash, and has the most matching properties like the Portland cement. Untreated PFA was found to be the best candidate for binder application in road subgrade and rammed art. So that PFA was the candidate material for us. The second one is the multi-cyclone fly ash, has very high porosity and low cementing properties. It is best suited for applications related to carbon capture technology and soil amendment composting, because it's more like a granular material. And then the last one is the bottom ash, is a good substitute for coarse and fine aggregates in the rammed earth, concrete, and road base. So it's not providing the strength or anything, but it was helping us with to support with the fly ash and other materials that we are using in the rammed earth or the road subgrades. So by looking into those conclusions, we have come up with a few objectives in this work that we have collaborated with pulp and paper mills in British Columbia. So looked into the characterization, toxicological analysis, and that what I have already described, and 3 different types of fly ash, multi-cyclone, precipitator, and the bottom ash. And the second one is to develop these ash-based construction materials. We are using into 2 different applications. One is the rammed earth, another one is the road subgrade. And then looking into some field applications, a small scale field application related to rammed earth construction and the road subgrade construction. So for that, at the beginning of the project, we are searching for the industrial partner who will be excited as we were to test some of our materials in the field scale, and therefore we'll have a better understanding about field application, how it will impact when we are constructing them into real life situation. So starting with the rammed earth housing, why it is important for us, why we are talking about the rammed earth. When we have a good understanding about the rammed earth materials, I will talk about some backgrounds, the traditional rammed earth materials, and then we'll look into how we can improve those rammed earth and use them in the housing construction. The reason is that in our areas, somewhere in northern side of Canada, it's hard to have a good supply chain in place. Therefore, people are interested, the local communities are interested to build whatever they have locally and try to identify the waste stream available to their community and establish a housing system for them that is more environmental friendly, because the people would like to stay close to nature and not that typical high strength construction that we use for our high-rise buildings. So we need to know about those solutions that can be cost effective, sustainable, and then built by the indigenous communities. So that's our overall bigger ideas about working with this rammed earth housing. So traditional rammed earth housing, rammed earth material has low environmental impact because that use these rammed earth materials, we use naturally available products, and it provides high hydrothermal performance. Rammed earth construction possesses low embodied energy and high recyclability. And durability is a major concern for those traditional rammed earth, because water attack and frost damage in wet and cold regions, especially in Canada, we are talking about a huge changes of the temperature during the summertime and the wintertime, and also the moisture changes based on that. Variety of the raw materials is another challenge, because then you have to every time I understand the raw materials, sources of the raw materials, characterize them, and learn about their compaction methods and exposition to the water increase. Those are the things create complexity. But if you look into this passive house, we are calling it hashtag passive house, net zero, rammed earth, and sustainability. This rammed earth house is built in Summerland, which is a small city in British Columbia, 50 minutes from the UBC Okanagan campus, 50 minutes drive. So we compare the global warming potential for concrete and the global warming potential for rammed earth material. So these are the parameters we look into when we are looking into the impact of the greenhouse gases in the environment and what are the impact of those carbon dioxide emissions to the environment. So you see the values are much lower for rammed earth. And again, another parameter that we look into is the embedded carbon coefficient. Again, this is much lower for rammed earth. So this is the parameter calculated based on the per meter cube of the material for made out of concrete and made out of rammed earth product, traditional rammed earth product, and also it compared with the Portland cement and the fly ash. So this fly ash value is coming from the typical fly ash that we see from the coal industry. This is not the one from this pulp and paper mill fly ash. So rammed earth in the modern industry, how we looked into the rammed earth. In modern industry, we are looking into the rammed earth with cement stabilization because that's the typical approach to improve any strength. And it will provide a good durability, but reduces the product sustainability because the goal of using rammed earth is to use rammed earth product as a natural product. So therefore, we don't have to worry about that sustainability component. But now, if you want to increase the strength, if you use the cement, then that has impact on durability, increases durability, but that reduces the sustainability component. Inherent sustainability compromised by the modifications using carbon-intensive material like cement. Key challenges is to develop a novel rammed earth technology with significantly low carbon impact and improved climate resilience. So we have to look into the low carbon impact and the carbon resilience material. And this is the wall constructed at our campus, a rammed earth wall in the UBC library building. This wall is not for strength bearing. It was only just for the decoration purpose, but it was built out of natural material, reduced cement use, and also just to remind everyone that reminding about the nature, close to nature, stay close to nature, and the sustainable, go for sustainable construction. So the experimental work we have been doing in our lab have made major attention over the period of time, because this is a waste product that British Columbia, government of British Columbia, industry of British Columbia, they are looking into find a solution. So we have our works have been noticed by many. Now we are coming to the little bit of newer component that we want to address, the durability part. Still, we want to use a small amount of cement rather than the higher percentage of cement that modern rammed earth product uses. But we want to see, can we use this fly ash and look into the thermomechanical performance? And we have used modified mold to test those kind of parameters that is important for the durability point of view. So this is the solid rammed earth specimen for strength and durability analysis. We looked into the durability and strength analysis and also the freeze thaw analysis of this material over a period of time. Then we have used this hollow rammed earth specimen for thermal analysis and used the environmental chamber with time lag and decrement factor, design with this sample, and also use the thermal conductivity apparatus for the thermal conductivity and a specific heat capacity. So this tester, in a process of publication, and my master's student completed the work, Kianush, and now graduated. So the thesis is also, we are keeping it not available to the public yet because we are waiting for publication to come out, and we'll be able to share that soon. Now, looking into the microstructure, we have to look into more than general microstructural analysis we do. When we make the modification, of course, we have to look into the XRD, then we have to look into the SEM, FTIR, and then we have to look into the chemical composition and the leaching, so that therefore we run the elemental analysis, ICP-MS, ICP-OES, those kind of tests, and I want to acknowledge those laboratory at our campus for the test element research. So if I just summarize what we have achieved by doing all the tests into two combined picture, because there are tons of data to share, but I'm just going to summarize them as a whole so that we can understand the overall outcome of this rammed earthwork. So we have used the fly ash as received, and we have used some calcium bentonite clay as additive, and we have looked into the UCS data, unconfined compressive strength, and we have looked into a several combination. So as you can see in our x-axis, we have a several combination of the materials. So I'll just explain what are those materials are. So the first one here is SC, which is 10% cement, Portland cement, and then that's how we are just refining them, 10% Portland cement. And then we have the S is referring to the raw material, the sand material that we use for building those rammed earth. Then we have SPC 55, that means 5% fly ash from our project, and the 5% cement. Then we have SPC 10.5, that means 10% fly ash and 5% cement. Then we have 20% fly ash and 5% cement. Then we have that Portland cement of 5%, fly ash 5%, and we have 1.58% of the bentonite material added to that. And then we have the 10% fly ash, 5% cement, and then 1.5 bentonite. And then we have 20% fly ash, 5% cement, and then 1.5 fly ash. So this is how we have looked into the data for 7 days curing, and the 28 days curing is the regular curing, no temperature was added. So we see that's the reference point over here, dotted line. So with the control material with that 10% cement, and then we saw the improvement when we have that SPC 5.5 and a 1.5% of bentonite. So we saw the increment of the UCS data, the compressive strength data. And with this arrow, we are also saying that we consider that as an optimum mix. We saw the 10% loss in the freeze-thaw testing. When we run the freeze-thaw testing, we have seen less than 10% loss of the strength. So that's why it is identified as our optimum for these given conditions. And we also see the other way to look into this example as in terms of the fly ash as geopolymer by alkali silicate activation. And then we saw the similar type of data over here with the reference. We saw the improvement after 28 days. And it's not favored in the colder climate because we saw more than 80% loss in the freeze-thaw cycle. So this is very interesting because when you are using the geopolymer alkalization, it improved the strength. And we have been looking into different data from literature that alkalization, the geopolymer process, geopolymerization is important to improve the strength. But then if you look into the freeze-thaw data, for this material, we see that we lose more than 80% of the strength over the period of time. Now, microstructure, we see the growth of cash. We call it cash in the pore space, which is the calcium aluminate silicate hydroxide. So that's what we see over here. This is the fly ash and bentonite, and the fly ash geopolymer. We see that uniform coating of the geopolymer on the soil surface without any void. So that's the impact of geopolymer. Now we run the test sample in Lake Country, another city beside Kelowna, and because the contractor who was building the rammed earth wall, they got a client in Lake Country, and they used our recipe, constructed the wall. So the only observation from this after a long period of time, because this was done in 2021. So when we constructed that, it was fine, but over the period of time, because of having some bentonite in this material, it started to show some, long-term environmental impact. Some small cracks started to develop after it faced several freeze-thaw cycle, natural freeze-thaw cycle from the weather point of view. This is a work published in related to rammed earth using fly ash as an alternative low carbon cementing material. So if you're interested to read more about this data, the initial data that I just showed, other than the thermal data is under review right now, you can have a look on to this paper. So our long-term research goal from this rammed earth construction technology is to, we want to preserving and improving its strength. That means durability and sustainability are important. And we want to overcome the weakness. That means we want to customize and make it flexible. So if you can pre-build them, the panels, use the 3D technology, and then that can be used anywhere. So they develop a smart RE building material with superior thermomechanical properties, high carbon capture capacity that can become an integral part of future building choices as part of its climate change strategy. That's what we want to aim for: develop prefabricated panels and blocks using conventional and advanced 3D printing, make our new building technology accessible as building option in modern cities for future green construction. Develop a design and performance guidelines, because that's what important, that's what drives people to go for the technology, and help to make this innovative construction more available to mainstream building industry and potential local contractors, and also the communities I just mentioned, remote communities. But then their approach should be different. They don't want to go with the prefabricated panels. They want to build at their own facility based on their sources. So with this, the major research finding from this rammed earth project was to we have been able to replace partial cement with wood ash, improve the thermal properties of the rammed earth by compromise both strength and durability, but we compromise the strength and durability. Combination of fly ash, calcium bentonite improve the mechanical properties. That means compressive strength and freeze-thaw durability above the levels of the standard cement stabilized rammed earth material. Using variety of local aggregates and adding bottom ash as a partial replacement for aggregates altered the strength significantly. And we also saw that adding fly ash increases the carbon capture capacity of rammed earth due to inherent chemical reactions such as calcium carbonation. So these are the findings from the rammed earth. Now I'll just move on to the application related to roads. So what we see for in Canada, climate change vulnerability on our road infrastructure. The reason is that this picture was taken from Yukon, one of the provinces in the northern side. The ice in ice wedge that is in the active layer, it started to increase because of the permafrost. So that means the soil is not frozen for a longer period of time as it should be, and that is creating the increase of the active layer. That means it started to active, so started to melt. and melting is causing the changes of the moisture, and this is direct impact from the climate change. And more examples here that we see the crack caused by permafrost thaw on the shoulder of Alaska Highway in Yukon, runways and taxiways in the international airport and wrapped due to permafrost thaw in the same province. So those are the reasons where we are looking into how to improve the quality of the soil underneath so that we can have a better road infrastructure, and which is a key thing for many activities, especially for the food supply chain. The roads has to be, roads infrastructure need to be intact in Canada. So what we have used, we looked into the optimization of the fly ash binder for subgrade, and I will just go with that again, how the compressive strength over the period of time with respect to different combination that we have shown here. For 7 days UCS, 28 days UCS, and the dotted points are UCS ratios between the 28 days to 7 days. So we have untreated fly ash. We have 3 different types of combination: 10%, 20%, and the 30%. So for this type of fly ash, you see that we have MFA and also PFA. So we have used both type of fly ash from the pulp industry, the multi-cyclone and the precipitator fly ash. So the first one here is MFA, which is the multi-cyclone fly ash. Then the similar percentage of the precipitator fly ash without any treatment. So these are the untreated ones. These are the most valuable ones because if you don't have to treat them, it's more cost effective for application and easier to use. The third one here is a combination of multi-clone and the precipitator fly ash, but it doesn't help much, as you can see from the UCS data. And the last one is the PFA with the geopolymer. So as you can see from our untreated PFA, we got very high values for compressive strength for the 28-day sample. And we also see the ratios is very close over here. Now, if you look into that behavior in terms of the compressive strength and the fly ash as received, we are looking into our desired value for the subgrade strength is between 450 to 600 kPa. And now we see this 20% one is the most economical ash content, which is 20% fly ash, the precipitator fly ash. And then we see the optimum ash content for pavement subgrade is 25% based on our data. And also we recommend ash content for unbound road is 30% because we don't have to go for the final, development of the roads. Is unbound, unpaved roads, we can use 30% fly ash. And that work was published in Journal of Clean Air Production. So you're welcome to have a look if you're interested in the subject. And now we are looking into this work also grab attention because we are talking about taking the fly ash, not sending into landfill, but making it available for other uses. And we have demonstrated 2 different types of applications. One is for the rammed art construction, which grabbed a lot of attention from the local community. And the second one is the road subgrade. The typically road construction, the one at the surface where we are looking into British Columbia or all over Canada, based on the temperature changes has impact, and therefore your subgrade material need to be treated so that you can find out some industrial byproduct based sources so that you can use them and treat them and don't need to replace those subgrade materials with some foreign materials, which can be very costly. So that's what we have here. Okay, so now we are looking into a test site for service road construction in Kamloops landfill area. So the reason we have this site picked up because this is the site for one of the landfills, one of the pulp mills. That was the closest one for our campus in Kamloops, and they were building a connecting road in at their site. So they asked us whether we can use our recipe and then work with the contractor and then start to see the performance of the road. So we have used the simple, fly ash bentonite combination with the right amount of ratio, water ratio with the binder ratio, and then properly mix them with the help of the contractor at the side. Allow those material to be laid out on the surface of the unpaved road, and then roller was used to compact them at the side, allowing moisture as needed based on our design, and then use the drum roller to compact them at the end. So the service road is performing well since then, other than at some extreme weather condition, we see some of the issues related to small finer cracks, but as expected, when we have a extreme climate condition, then we can see those impact of the freeze thaw cycles on the soil, underneath soil, and therefore we can see those kind of small cracks develop on the surface. But so far the road is in good condition and staying there for helping the facilities to use the connecting road. So I have used a list of journal articles that I have used for this presentation with the references from our research group and conference proceedings. The conference proceedings in the National Canadian Geotechnical Society conferences, that means you need to have a peer-reviewed article presented at the conference, and full article reviewed by the peers expert in the field. So therefore, these are also valuable contribution from the research group. The second, the one of the items that I want to identify here, the thermal inclusion, insulation enhancement of the rammed earth is under review. So hopefully we'll hear that soon about that article. And I use MyTex Global League to attract international undergraduate students to come to my lab, work in the lab during summer. So this is the link for the article published based on the last year summer interns came from, two of them came from India, one came from France. So this is a good option to look into if anyone is interested to come for a visit in summer, work in the lab, and join the lab and get some work done. They were very supportive, and their work was working with the PhD or the senior master's student. Their contribution will be published and acknowledged. And the work supported by different pulp and paper mills. The list of pulp and paper mills are provided here, and because it was an alliance between UBC and the paper mills and the FP Innovations, who are the key player on in this sector. So we had many contributors from that, and under the BioAlliance, we have worked on this project and is still working on the project. After that, NSERC, the federal funding government agency that we have in Canada, supported our project, and also MyTex, which is again the local government funding support system. Both cases, we need to have 50% support coming from the industry partners. So that's also valuable, acknowledging them. And Innovative Art is the contractor for the constructing rammed art, and supported all the way with the financial support and also the support of their in-kind support from their staff support and their manpower support, so that we can build those walls in the Lake Country. So if just to get into the point, I promote a diverse group. So if you are interested, if you have the right background and excited to work in a team who are diverse, so maybe you can also think about connecting with me, and that would be interesting. We can talk more about that. If anyone interested, please email me with this address over here. So stop here and start to look into the questions. If sure, we can start looking into that. Thank you.
Thank you, Dr. Sumi. So now there are a few questions. So let's discuss first. So it's a different experience altogether for me because you are talking about a material which now previously people were using, but now using earth, rammed earth in this part of the world, people are not, but that's really interesting. Okay, so
Yeah.
the first question, where is it? Okay. There is first question from Dr. Surbi. In the optimized RE wall, how much percentage of fly ash is used as a binder? And do it help for carbon capturing?
Okay. So for the binder that we have used here shown is 20%. So 10 to 20% give us a good results. And then the carbon capture component is also currently being progressed. So I have a PhD student working on that. It's continuously changing. So we have used that range around 10 to 20%, and that provided good results. Yeah.
Okay. So then another question is there. Hello, madam. How to quantify the percentage of each mineral in fly ash?
Yeah. So I have talked about those over here, a list of different tests you can do. XRF is the one which gives us the chemicals. Mineral composition can come from XRD. So it's a combination of both. It'll give you a good understanding about all the minerals and the chemical composition.
Anybody else? Okay, so this is really interesting to me also. When I fed 62% of calcite. Oh, so it's a good amount of lime is
Yes.
there.
Yeah.
Oh, that's good. So that's why maybe, I mean, it is a temptation to use it.
Yeah.
How they are incinerating, it's not polluting anything like in pulp when they're coming out of the industry. Mostly my experience that area in and around, I found lots of bad smells come out. But then in that case of when they're going for incineration, so they have got the internal plant.
Yeah, they have the internal plant for all the facilities, but then they produce a lot of waste, right? So they don't have that kind of a storage facilities. They need to find a solution because storage is a big deal. Like if you
Yes.
produce 1 million tons per year from in Canada, it's a huge. If you don't want to use this waste, you can dump it to in freelance. In Canada has tons of them, but then you have to take them. So then transportation cost will be much higher. So that's not useful for those mills. Another important component for this pulp and paper mill industry is lignin. So people are looking into lignin, how they can use that lignin waste into package production or even road pavement. So I haven't worked with the lignin part. I just focused on the fly ash component. So they produce different types of waste, as you can see from this diagram. So that can be revenue generator for them if they can find a good solution for their use.
Yes, this lignin that is also coming out as a byproduct from their plant.
Yeah. Yes,
okay.
That's correct.
So,
yeah.
Then you said 2 types. Okay, one more question. There. Andhika Saputra. How about mineral content of MFA?
We didn't do all the mineral content of MFA because we already found out that PFA is more attractive for us. But if something comes up, we can always do that. It's not a big issue. We can just run some XRD and then find out. Yeah, that was the reason we haven't.
Next question is from Deepak Patwa. Why not shear strength of the modified samples were evaluated as in the road pavement application? Shear strength study required instead of UCS for the designing.
Yeah, because shear strength was in detail geotechnical properties, which is the next step. If someone is going for the application, you need to go for all the geotechnical element testing. But all those material improvement characterization requires one test. Indexed is a test, that is the UCS test used worldwide. Yeah.
Yes. Then next is Avik Kumar Mandal. It's interesting, informative, and thoughtful talk. Professor, was there any study on the use of bottom PFA? I mean, for
Yeah, bottom
stabilization
ash.
of the expansive clay subgrade of road. Okay.
We just use the bottom ash to supplement replace the voids, like, instead of using other kind of aggregates, we just try to use that bottom ash as a different, either it is rammed out or the roads we have used as a supplement material, but not the main focus. But then in my lab, we are right now in so many different areas, we are working with this fly ash. It's just like a gold mine for us right now. So we are using for landfill, we are using for plant growth facilities, we are using for rammed out, we are using for roads, we are using for carbon dioxide sequestration. So many different applications. And if you just stay tuned and look into our publication, you'll see that we are producing many in that direction. Of course, there are opportunities.
Yeah, these are really challenging.
Yes.
And this is also really interesting. That's what I always say. Because we have no information, we are saying waste. Once you get information, it will be waste. One more question from Dr. Survi. Does fly ash help for thermal conduction in the fly ash-based rammed earth material?
Yes, we saw good performance of the thermal properties. As I said, that because it's under review, that's why I didn't share those data, but hopefully I can share that with you, Shurvi, after we have the publication accepted, for sure.